Here I want us to look at a problem that we can solve in a number of different ways. Well, two come to mind. We can either use energy conservation or we can use torque. And I don't think one is necessarily easier than the other. I just want you to see the two ways and the kinds of things we get from those. So this is a big disc pulley, if you like, that has a mass hanging from it, and that mass, we start at rest, the mass falls, and this pulley unwinds. And so it falls some distance h, and we want to find the v or the omega once the v of the mass or the omega of the disk once it has dropped a distance. And there are no numbers here, so we're just going to do it in terms of letters, which I know is everybody's favorite. So even though it's set up so we can do it from an energy point of view, I've already got an H and I can see some potential energies. I'm going to start with actually the torque point of view first. Just because it's a little less familiar and I want you to see how it works with force diagrams. So if we're going to use, when I mean the torque approach, I really mean we're going to use F equals ma for the box, for the mass, and for the pulley or the disc, we're going to use sum of the torques is equal to I alpha. Okay, so for the box, we've got a fairly simple situation. We've got tension that's up. We have mg that's down. That must be bigger because it is falling, right? So mg is bigger. It's falling. It starts from rest and starts falling. So we do have an acceleration that's down. And it turns out that it's a little easier if we just say the down direction is our plus y direction, which I know is a little odd, but it just makes everything a little easier because that just shows you that our F equals ma, we've got an mg minus the tension equals the mass times the acceleration, right? Because this has to be bigger than that. That way we don't have to worry about too many signs. So that's our F equals ma equation. And so we already know we've got two sort of unknowns. If we can find an expression for the acceleration, it's going to be constant, so we should then be able to find our v with our constant acceleration equations, right? So if we have I'm going to put this over here, if we know a, the acceleration, then we can say, and we know this distance, we can say, hey, this is my v0, which is 0, my v final, so I can say v final equals, v final squared equals v0 squared plus 2a, the distance that we go. In this case, it's h. So if I know a, this is 0, then I'm basically done with the problem, right? V squared is equal to 2ah. So I can just take the square root of that. Okay, so our job is really to find a. And okay, we're partway there, but we have this tension, and that wasn't one of the things in our list that we could leave it in terms of. So now we're going to look at the pulley. And so in the pulley situation, here's R. On the pulley is being pulled by this mass, but it's actually, you don't want to write down it's the mass. It's really the tension that's pulling it down, which means it's less than the mass, right? Because the tension has to be less than the mass. If they're equal, then the whole thing just sits. There's no acceleration. So the tension is pointing down. Here's our radius. So we've got R and tension, and those are at 90 degrees. So the magnitude of the torque is just going to be R times the tension times sine of 90 degrees, which is just equal to R times T. So that's pretty nice. The tension, torque created by the tension is going to be in the same direction as the angular acceleration, because this is going to be the direction of omega. We're going to have it spinning up, so that's the direction of rotation. So if we use our right-hand rule, that's into the page. So you can just double check omega and alpha are going to be into the screen, your computer screen. And if you do R cross T, that's also into the screen. If you use your first finger along R, your second finger along T, you'll get something that goes into the screen, right? Okay. So putting everything into this equation, getting rid of the vectors because we've checked all of the signs just like we did down over here. So we get r times t is equal to I times alpha. Okay, well that didn't help us very much. R and I are allowed according to the variables we can use, but alpha is not. But we've got a connector here. Alpha is your angular acceleration, how much it's speeding up its rotation. But if we've got something with an alpha, right, at this point, this is its angular, so omega's, we've got speeding up in that direction and alpha is speeding up. We can say that alpha is equal to this A tangent, right, the tangential acceleration, AT, ooh, that's a little hard to read. We would have an AT there, AT over R. And that point has to be accelerating the same amount that this mass is falling down, because otherwise the string would have to stretch, right? If one part of the string is going, has a different acceleration than the other part, then the string is not going to be staying the same length. And so we can plug that in here. RT is equal to I AT over R, and realize this AT is really the acceleration of the block. So I can solve for that. I've got the acceleration, well actually I'm going to want to solve for t because I want to get rid of t here. Because I want an expression for acceleration, but t is no good to me. So tension is equal to I A over R squared, where this A is basically my tangential acceleration. So I can erase that and put this right in here. And so now I can substitute this in here, and I've got an expression with a little bit of algebra that allows me to find the acceleration. So I get mg minus I over R squared A is equal to ma. I want to solve for a because I want it in this equation. And so that gives me mg is equal to, I'm adding this to both sides, a plus ma. Now I'm going to factor the a out of both of these equations. I get mg is equal to I over R squared plus m times a. Notice the units are okay because moment of inertia, this I is mass times a radius squared with some factor depending on what kind of shape this disk is. So this has units of kilograms. This has units of kilograms. So that's all good, okay? And which means this right side is newtons and the left side is newtons. So that's good. And so I can solve this to give me my acceleration is equal to mg all over m plus I over R squared. Okay, it's hard to make heads or tails out of this, but I want to point out a couple of things. This is like a checking your answer kind of thing. If your moment of inertia is going to 0, in other words, the disk doesn't have much mass, or we ignore it, like we've done before in previous situations. If the moment of inertia heads to 0, then notice that your A is just equal to G. And so if we look at this setup, I'll just redraw it over here. That just means this unspools and this falls with an acceleration of g, because basically this disk has disappeared, right? If your moment of inertia is very big, right, if it's a really massive disk with a big radius, then you can see that this is going to be, this term right here is going to be big, which is in the denominator. It will make your acceleration very small. And this mass won't fall very quickly. It won't pick up speed very quickly. Okay, after all is said and done, we really just need to stick this A into this equation, and then that gives us our V. So altogether, this is a really messy equation, but if you had the numbers, it would be pretty easy to plug everything in. I've got V is equal to 2mgh over m plus I over r squared. I got to take the square root of that. So that's my speed. Okay, so that's using torque. So that's a little involved. Let me go through just quickly the energy approach, because this is really set up a little better for energy because we're asking about speed and we're given a height. But there's still some things we need to worry about here. We've got m, this is r, this has a moment of inertia I, and then we're allowed to leave it in terms of m, g, I, r, and h. Okay, we can set up our energy situation. What I would do is I would call this my bottom part, my y equals 0, so that I can measure all my potential energy from there. So my energy initial is going to be, well, my kinetic energy is equal to 0. Nothing's moving. My potential energy, well, for the box, for the mass, for this little mass, it's equal to mgh. The potential energy of the disk, it's sitting there, so of the disk or the pulley, is going to be its mass of the pulley, g, and now I got to label this as sort of h2. h2. Okay. Energy final. Kinetic energy. Well, I've got kinetic energy. For the box, it's going to be 1/2 mv squared. It's not rotating, it's just falling. But the disk also has kinetic energy. It's rotating. So for the disk, this is 1/2 I omega squared. And then potential energy, well, for the mass, that's 0 because it's hit the y equals 0. The potential energy for the disk, it stayed the same. It didn't fall down. So it's mass times g times h2. And so I need to equate these. And so that gives me mgh plus mass of the p. That should be d, I guess, for disk. Oh, pulley. Okay. Big M, gh2, is equal to 1/2 mv squared plus 1/2 I omega squared plus big M gh2. And now this, you may have been worried about that because we didn't know h2, but those cancel out, so it doesn't matter. And then this just gives us our expression, and you think, oh, we've already got our v, and we do, but we also have our omega. And so we're going to do the same kind of trick we did before. If we know our v at this point, or actually I guess it's 0 there, but down here if we know our v, then so the string isn't stretching, same thing needs to be true. Our v at the edge needs to be the same, and so we can recognize that when we have something rotating, right, there's a v in this direction and an r, we can say, hey, our v is equal to r times omega, or omega is equal to v over r. We can put that in here, and now we have mgh is equal to 1/2 mv squared plus 1/2 I v squared over r squared. And I can again collect terms. I have multiply both sides by 2. I have 2 mgh is equal to m, and I'm going to factor out a v squared as well. So I multiplied by 2 to get rid of the 1/2, which gave me the 2 there. And so plus I over r squared times v squared. So v is equal to square root of 2 mgh over m plus I over r squared. And I think that gives us, yep, the same expression that we got before. So this second way is easier, as is often the case, but I wanted you to have a little bit of experience seeing how you can set up the torque equations to get exactly the same thing.